picking up where we left off, the possible values for our three new quantum numbers, capital L, S, and J, can be obtained by what is called a Clebsch-Gordan series. All of the possible L's are going to be somewhere between the one particular L and another particular L, and the absolute value of the difference between them. And the same thing for L. Same thing for S. And then J is going to have possible values between L plus S and L minus S, and that's an absolute value issue. And I realize that we're getting into some new terms and some new quantum numbers here. So those letters and numbers may not have as much meaning for you as we would hope. And so I'm going to do some examples with that coming up. So, for example, the titanium atom, if you look at titanium's electron configuration, it ends in D2. And so a question that comes up is, what possible L values do we have for titanium? Well, a D sublevel has M sub L's of 2, 1, 0, minus 1, and minus 2. So we could have the largest possible L is 2. And in fact, the largest possible L's are both 2. It's not a stable configuration, but we could envision both of those electrons, one spin up and one spin down, being in the M sub L equals 2 position in that D sublevel. And if that's the case, the L would be 4. Or we could have the electrons separated so far that one of them is in the 2 and the other one is in the minus 2, and L would be 0. And in fact, using the Clebsch-Gordan series, we know that if 2 plus 2 is 4 and 2 minus 2 is 0, then the possible L values for ground state and excited state are 4, 3, 2, 1, and 0 there, every whole number between between M sub L plus M sub L and M sub L minus M sub L. So we can do this again for L for nitrogen atoms. Let's make sure I'm popping up. There we go. What are the possible L values for nitrogen? And again, the most stable configuration would have one electron each, and M sub L 1, 0, and minus 1 would add up to 0. But we could put them all in, not all, but we could put 2 of them in M sub L 1 and 1 in 0. So we could have an L value as large as 2. So let's work this out with Clebsch-Gordan. In order to do this, since we have 3 electrons to deal with instead of 2, we're going to have to do it in steps. We couple the first 2 electrons. So their possible L's for just those 2 are all the whole numbers between 1 plus 1 and 1 minus 1, since 1 is the largest L. And so we get L prime for just the first 2 electrons is 2, 1, and 0. Then we've got to couple a third electron to that. So we'll treat the L prime as a possible M sub L. And so we could have L's of 3, 2, and 1 by coupling with L equals 2. We could have L's of 2, 1, and 0 by coupling plus and minus 1 with the capital L prime equals 1. And then we do the same thing for 0. Since we have the absolute value signs there, we can only get 1. And so the possible L's for nitrogen are going to be 3, 2, 2, 1, 1, 1, and 0. So there's a total of 7 different states with those various L's. And so what we're going to want to be able to do is summarize the quantum numbers, the important new quantum numbers, for a particular state. and be able to compare those states without really having to do the heavy-duty mathematics. And the way that we're going to do that is with a term symbol. A term is a group of states that has the same L and S values. The difference in energy between quantum states that have the same term is very, very small compared to the difference in energy between quantum states that have different terms. So we'll be able to predict the most stable position, the ground state, for a particular atom based on its term symbol, and how different, how significant, we'll be able to order the excited states based on their terms. So like I said, a term symbol is an abbreviated description of the angular momentum quantum numbers for a multi-electron atom. It's related with the energy level of a given electron configuration. L to S coupling is assumed, and the ground state term symbol is predicted by Hund's rules. A term symbol then has that spin multiplicity number as a pre-superscript. So it's going to be S times 2 plus 1. So when you have one unpaired electron, spin is 1/2. You're going to get a 2 there. If you have none, then you're going to have 2 times 0 plus 1. That would be a singlet state. And then L, whatever value you get for L, is going to be the main part of the term. And then a subscript, a post subscript of J to round out the full term symbol. I've already defined that. L is the sum of all the M sub L's in the highest energy subshell, and is assigned a letter analogous to those used for orbital designation. So for example, if we get L equals 0, then we're not going to write 0 here for L, we're going to write S. If we get L equals 1, we're going to write P. If we get L equals 2, we're going to write D. But it's going to be capital. We're used to using lowercase letters in our electron configurations. In term symbols, we're going to use capital letters for L. And then, as we said, J is going to be the absolute value of the difference between L minus S. For a half-filled sublevel, it's going to be L plus, it's going to be L minus S for a less than half-filled subshell. So for example, if we're talking about a P subshell, if it has 2 electrons or 1 electron in it, we're going to use L minus S. If it has 4 or 5 electrons in it, we're going to use L plus S. And if it has 3 electrons in it, we're just going to use S, and that's what's going to give us the J for each term. Alright, so let's try this for a particular example. We can calculate the term symbol for, this is one we've already tried, for a fluorine atom. Fluorine has this electron configuration that we remember from general chemistry. It has 1 unpaired electron, so S is 1/2, and 2S plus 1 is 2. And we can see, the electron configuration orbital diagram there. L, we've already added up for this, is 1. So the capital L being 1, that refers to P. And since the subshell is more than half full, J is going to be L plus S, and we get 3/2. And so the term symbol looks like this. 2 as a pre-superscript to describe the spin state. P as the main part of the term to describe the capital L, the angular momentum, the coupled angular momentum, and 3/2 for J. Now the question comes up, why do we want to do this? What does it tell us? The consequences of term symbols is that it gives us a result that basically is Hund's rule. The lowest energy term is that which has the greatest spin multiplicity. So for example, if we're in a position where we have 2 electrons in a P sublevel, the possible terms are 3p with particular J, 1d, 1s. 3p is the lowest energy of these because it has the largest spin state. For terms that have the same spin multiplicity, so for example, we could put an electron in L equals 1, m sub L equals 1, and an m sub L equals 0, then L would be 1, or we could put one in m sub L equals 1 and m sub L equals minus 1, and then L would be 0. So we could get an S or a P for the triplet state. The terms that have the same spin multiplicity, the greatest orbital angular momentum has the lowest energy. So a D term is lower in energy than an S term. So basically what we're doing to evaluate a particular electron configuration's term is we're looking for the largest spin state first. If the largest spin state is a tie, then that tie is broken by the largest capital L, the furthest along in our old orbital designations. And then there are selection rules for transitions that can happen from term to term. So our selection rules can be put in terms of term symbols. Delta S is going to be 0. So if there is a change, and keep this in mind when you get to the multiple choice questions on this chapter, because this slide is going to give you the answer for at least one of those questions. S doesn't change from a normal transition. So if you see S changing, that's going to be a forbidden transition. Delta L can be 0 or plus or minus 1. And so we can, and delta J then can be 0 or plus or minus 1. On the other hand, though, J will have to change if J is 0. So we can see a J equals 1 to J equals 1 transition, but we can't see a J equals 0 to J equals 0 because there's no angular momentum being absorbed in a J equals 0 to J equals 0 transition. And so those are the selection rules for these kinds of atoms. So watch for that in the multiple choice question that pops up in this chapter. These rules break down just a little bit for larger atoms. So these rules are true in general, and they're definitely true for atoms between helium and atoms with about 40 electrons. When we get to larger than about 40 electrons, the J to J coupling becomes a bit more noticeable, and delta S transitions of plus or minus 1 become possible as well. So just a little bit of a hint on that. In fact, I'll put that up on the slide. This is an abbreviated set of slides from Chapter 11. There's some things in the book in Chapter 11 that you can read if they look interesting to you. Helium, neon laser, I think, and some other things that are consequences of atomic structure. We don't have time to spend time on that in this course. Even in a full semester, we wouldn't, because we want to get to, as chemists, molecular quantum mechanics, and that's what chapters 12 and 13 are going to be all about. So we'll pick up there with our next video.